Okay, thanks everybody for coming. I'm Hank Leininger, and I'll be talking about interesting and dangerous things to do to a source code repository. All right, this is weird. If it's this far away, you can't hear me at all. If it's this close, I'm gonna kill you all. So I'll just have to try to remember to hold it somewhere reasonable. So just some of the stuff we'll cover, I'll give you a little bit of background and then talk about some source code repository tampering vectors and then some examples for different SCMs. And then a little bit about compromises that we know about and possible mitigations for the strategies that I will have described in the beginning. So just a little about me. I've been building stuff and breaking stuff for quite a while. I was a co-founder of CoreLogic. If you've heard of me or of CoreLogic, it's because of the Crack Me If You Can contest that we run at DEF CON every year. But also for the last few, and I've given a number of talks on that kind of stuff, and so have some of my coworkers. But also for the last several years, we've been working on some SCM tampering-related research for DARPA. Also in my copious spare time, I run the MARC mailing list archive site, which is another way you may have heard about me but not have heard about me. So what is an SCM? It's called a lot of things: source code management system, version control system, software configuration management, which has the same acronym. For my purposes, I'm pretty much talking about the same thing with maybe one or two exceptions that I'll make clear later. By whatever name, an SCM is a place you put your code to not forget about it. So what do SCMs track? Well, they track changes, but what do we mean by changes? They track who made a given change, who checked it in, what was the actual change, the code, the diff, whatever, when, well, that's obvious, and then the log message that the developer added when they committed it. Actually, I should ask a show of hands. So how many of you consider yourself primarily a developer? Like you spend at least 50% of your productive time developing? Okay. How many of you have used an SCM of any kind, whether you were the admin or just a user? Okay, SSCS. Okay, well, specific ones. CVS? Cool. Subversion? Git? Probably every single hand. Okay, that's kind of what I expected. Now, I'm going to draw some distinctions occasionally between the way you might see and use an SCM in a corporate environment or some kind of closed source development environment versus open source environments. The open source environments usually have their SCMs internet exposed, and in fact, some companies have businesses around exposing them. So there's a lot of different SCMs. The ones that I'm going to talk the most about are Subversion, CVS, and Git. But there are many more, and those are just the free and open source ones. There's also lots of proprietary SCMs. So in general, no matter what SCM we're talking about, there's a workflow. If you can see my mouse, yes, all right. So we have developers, they write code, they check their code into the version control system, whatever that version control system is. On the back end server, they don't get stored as application.c and startup.c. They get stored in whatever format the VCS or the SCM uses to store its metadata. And it's different for each SCM type, and the differences in the details do matter, but not until later. They check their code in, they check out the code, the updates from their other, their coworkers, whatever. Whatever it is, they're building some kind of thing, a widget, app, or perhaps they're using it to maintain configuration information for their enterprise, not even using it for software, like for source code, but for config files. That's cool too, because large enterprises have lots and lots of config data to keep track of. Some environments may have a code checker in the mix as well, so that when you commit code, it gets run through some kind of source code analyzer, or before you do a production build and do a release, you send it through some QA process or whatever, and that has feedback back to the developers. There's, in addition to, as I said, in addition to code being homed inside an organization, there's a lot of public sites whose entire business model is hosting projects for people. Some of them also have enterprise-y flavors, like there's GitHub Enterprise, or there's other, you can pay and have a sort of a closed version of the free public one. So why would you attack an SCM? The same reason you rob banks. Code is where the money is. You do all kinds of things if you get creative and you're successful at it. And by the way, I'm not focusing on, well, I'll hold that for a second. But there's all kinds of interesting things you may want, you may have as your goal. You could be targeting the organization itself. You know, I want to have a permanent way to subtract half a penny from every bank account ever in the whole world, but I'm not going to be dumb and drive a Ferrari to work the next day and get caught. So I've identified a really high value target and I want to go after them. Or I've identified a really high value target and I can't get there directly, but I know whose software they run. So I'm going to go compromise somebody that develops software that target of mine uses, and I'm going to backdoor the software so that once it gets deployed in my target, I will own my target. Various things an intruder might want to do when tampering with an SCM. They may want to lie about who made a given change the author of a particular commit message. Maybe they've compromised a certain developer, but they don't want you to know in the inevitable eventual incident response investigation. They don't want the developer whose account they've compromised to have their account identified as the vector. So they may want to lie about who made the commit of interest. They may want to change what changed, as in rewrite the history of an existing commit so that what you thought was the code you were shipping is no longer the code you were shipping. After it passed the QA tests, the bad guy changed the code in your repo so that now you check out the code and build it and ship it, and it's not what you thought. To cover up their the evidence trail again further, they may want to change the dates of a commit message or whatever to obfuscate the timeline of their compromise, or change the log message about a commit so that it fits the new rewritten history of, you know, they introduce a bug and they add a commit message that says fixed a bug or something interesting like that. So what can an attacker do? Well, we have to categorize first what kind of attackers. I'm going to talk about two different kinds. An attacker who has the ability to commit code to a repository, but that's all. They don't have any under the hood access. They're just like any other developer. Maybe they are a regular developer and they're just malicious. Or maybe they've compromised a developer. And the other is an attacker who has file system write access on the repo server. And they can monkey directly with the contents of the repo server, the metadata on the back end. So an attacker with remote-only access is restricted to doing things that the repo tool in question, whether it's Subversion or Git or CVS, allows them to do. And those things vary based on both the tool itself and how it's been configured in the enterprise. But there's typically things that they can do that are interesting to the attacker and therefore dangerous to us. Various ways that you might get that kind of access: compromise a developer's home machine or you know, their workstation. You don't need to compromise the back-end server if you can inject code by compromising the developer's regular account. Or especially in the case of public repo servers, there's typically some kind of web front end that you can use to manage access to your repos and whatnot. So if you were, let's say, running a vulnerable version of Ruby on Rails and somebody used that to compromise your repository and add themselves as an allowed committer, not that that's happened. Anybody remember what I'm talking about? Okay, I'll dwell on it more later. Now, somebody with file system access on the repo server can do anything that the repo software itself won't puke upon encountering. And you may be surprised to find later that there are a lot of things they can do without causing any noticeable breakage in the system. They can rewrite old revisions. They can hand push a revision onto head, and I'll show you why that's interesting. And obviously they can scrub, just like any other breach, they can scrub logs to cover their tracks. You might think that you have to be, like, let's say, gain root on the repo server in order to have that level of access, but not necessarily. For instance, if commits are done over SSH, the developer's UID probably has write access to the repo server contents on the remote machine. It's just that their access is restricted to only run SVN serve or whatever. Unless, of course, you have something that breaks the internet like shell shock, and your SSH authorized keys forced command stuff allows the attacker to run whatever they want because of the bash bug. Or there might be an unrelated infrastructure flaw. When we do internal pen tests, we often find 10 different ways into, well, every server in the enterprise. And what better way to stay resident if you're a real bad guy than backdooring the code before you leave so that they can kick you out, they can close the way you got in, it doesn't matter. You're there for life. Now, this is where distributed version control systems, there's an important distinction here. By their very nature, every user of, let's say, Git has a local copy of the repository. So it's not difficult for an attacker to get repository file system access. But on the other hand, those repo tools, hopefully, and in Git's case, definitely, they are much more strongly resistant to local tampering than old school things like CVS and Subversion. All right, that was get interesting. So I'm going to run through a bunch of different examples on a few different SCMs. I will often reuse a few things. A set of developers, one or more legitimate developers, Alice and Bob, will be legit developers who are not malicious and don't want to get owned. And Mallory is a malicious developer or perhaps a compromised account. And I'm going to over and over reference a project named foo and a source code file named foo.c because I lack imagination. And we will have one or more legit revisions, just super simple example here of some, a program that does a printf, yay. More than likely we'll have at least one other revision, and let's say that one does a fgets to read a buffer from a user and then includes that in a printf statement. And, simple, stupid, not terribly insecure. And then the attacker is going to want to modify that or cause to be reactivated a revision that uses unsafe gets, in my stupid example. Now, it's important to caveat this. I'm not focusing on what is the malicious code in question. Like, there's the underhanded C contest for that. There's the underhanded Perl project, which some would argue is Perl. For my purposes, I am not dwelling on that because other people dwell on that. We have approaches. They may or may not be solutions, but we have approaches to trying to find bugs by doing static analysis or by doing binary analysis, whatever. I'm interested in how does somebody deliberately get that bug in there without leaving an obvious trail or without being detected. So for my stupid examples, I'm going to be using I'm changing this fgets to a gets, and therefore, if anybody remembers gets, it's basically buffer overrun city. If you, I think pretty much the man page says, do not ever use this. In fact, if you try to compile something with a recent GCC that uses gets, GCC will complain at you and tell you not to do that. You know you're doing something wrong with the compiler. Doesn't say, your code is broken, but says your code is broken. So a few examples I'll run through CVS. CVS is sort of oldie but goodie, but it's really simple on disk format, so it's very easy to explain. First, I'm going to alter an existing revision. This is something that you would have to have file system access to do, or some other way to access the CVS server's underlying data. Just to explain it a little bit so that this makes sense, CVS stores data for files that it's tracking in these files called .v files. And every file in your project has a corresponding blah, 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 .v on the remote, on the back end. Those .v files are in RCS format because even older than CVS is RCS, and CVS uses its disk format. Inside foo.c will be the current revision. Well, actually, will be a bunch of metadata bookkeeping goop, and then the current revision in its entirety. And then a set of reverse or backwards diffs going back from there to older and older versions. So when you say I want to check out the original version of some file that's currently on version 1.10, what actually happens is it starts with 1.10 and then subtracts or replays all the deltas going backwards till it gets to the one that you asked for. If you're careful to respect the format, you can make a change in place to the .v file, no problem, to change the current head version. And or you can change an old revision and then change it back again before we get to head, so that somebody who checks out head doesn't see anything different, but somebody who checks out a previous revision or a previous tagged version, let's say, gets the wrong contents. So here's an example. We have Alice. She's sitting in her sandbox where she's been developing code. And in her foo.c, she's got an fgets, which is safe. Now Mallory on the repository server, because remember this one requires repo disk access, literally just all she has to do is change the line in the .v file, because the payload in the .v includes the text of the file being tracked. And Mallory is done. Now when Bob checks that code out, Bob gets the version that has the gets in it instead of fgets. Now that's bad. This is worse. Bob then makes some other trivial change to the file and commits it. The next time Alice does a CVS up, without telling her that, hey, you know, the revision that you were previously sitting at is now different from what it was before. Basically, Bob, having pushed a change or committed a change, has whitewashed the hand futzing that we did, and so Alice gets the malicious code back. Boom. All right, so that one requires file system access on the repo server. Let's go for something that you can do, and actually this one pretty much works with any revision control system that we've looked at. Move a tag to reintroduce a bug. Now tags are sort of symbolic names for, you know, release 1.0 or whatever name you use. My code as of Tuesday, that's a perfectly valid tag name. Developers will use that as a shorthand to say, okay, whatever the hell version we were at when we shipped production version 2.0, that's the version I want. Give me the version that's tagged as 2.0. So suppose we have a code base where revision 1.2 has been tagged for release as v1_0 of our awesome product. But then in QA testing, we discover a bug. Well, instead of gets, we should have used fgets, so we should fix that. So they fix it and commit that change. That change becomes revision 1.3. And then the tag v1_o is moved to point to 1.3 instead, because we don't want to be tagging the vulnerable version. We want to be tagging the good version. And then development moves forward. You know, the developers keep going, so they start working on what will later become version 1.1 or version 2.0 or whatever. An attacker with just remote commit access can typically add and remove tags, because that's just another developer action that's expected. Well, it's fairly okay to move a tag forwards for the exact situation I just described. You fixed a bug, now you want your tag to point at the fix, you know, at the version that includes the fix. That's great. But nothing stops you from moving a tag backwards. So the attacker who's in this development community can watch the code base as it's being, as it's evolving, says, that was an exploitable bug, I want that to ship. So the attacker moves the tag backwards to point back to the previous revision. Now, the next time somebody checks out version 1_0 tag, they're going to get the buggy version. Here's an example of this in action. So CVS status tells you things about stuff, and one of the things it tells you is what tags are on a given file. So Alice is sitting there, and she's showing that the safe, that the version v1_0 tag is tied to the safe revision 1.3. Mallory, using nothing more than regular developer remote access, simply rewrites the tag to point to 1.2. Now the next time Alice checks out, when Alice says, I want to check out version 1_0, the version she gets is the previous revision that has the bug. All right, hooks. hooks are server-side scripts or programs that will run whenever certain actions are taken by developers, like when commits are made. So you set up a log info hook that emails out notifications, or tags when there actually is a specific way to specific hook for tags and things like that. By default, when you create a CVS repository, anybody who has write access to the repository also has access to the CVS root directory. Hooks execute when you do a commit. By default, hooks execute as the user who did the commit. So what that means is, by default, anybody with commit access to a repo can run arbitrary code as other developers every time those other developers check in. To be fair, this is made explicit. This is pointed out explicitly in CVS documentation. They caution you, don't allow be careful who you allow write access to the CVS root directory. And in fact, certain other restrictions apply, or rather are optional, that would make you have to be a member of a specific group or something like that. But if you don't take that precaution, or if you develop for someone else's project, they probably have admin access in their own project, so they can run code as you on the repo server. So we'll walk through an example here where the repo server hosts several different CVS repositories. Users commit over SSH but don't have direct shell access. And again, we have Alice, Bob, and Mallory. In this scenario, Alice and Bob know each other, develop on each other's projects all the time. Alice doesn't know Mallory and doesn't trust Mallory. Mallory entices Bob to make some changes to her repository. And Mallory is going to use that to gain access to Alice's repo, gain access, in fact, to Alice's account. So first, Mallory sets up for her own project a log info hook, which means every time somebody does a commit, the log message generated is going to, rather, this script is going to be executed on the server. The log info hook will be executed anytime anybody does a commit. So Mallory puts a little one-liner in there that says, pretend this is an entire SSH key fingerprint, or public key, and same thing there. So she puts in a hook that says, anytime anything is committed to this repo, look in the authorized keys file for this public key, and if it's not there, echo it, add it to the file, to the authorized keys file. And then she commits that log info change so that the hook is now active in Mallory's repository. Bob makes any kind of change in Mallory's repository and commits it. Now, Mallory's public key has been added to Bob's authorized keys file. So now Mallory can check out as Bob's project, of which Bob is an administrator. Then she does the exact same thing to his repo that she did to hers previously. If her public key is not already in the committer's authorized keys file, add it. And she commits that. Now, Alice, next time she makes a change to Bob's repository, has just added Mallory's public key to her authorized keys. Boom. Mallory now controls Alice's account on the repo server. Now, that was a really, really simple payload. You can get way more complicated. You can also be a little bit less obvious than that, echo into authorized keys in the actual hook that you define. Hook files support some variable substitution and things like that. And so, and you can use them, for instance, to reference the file that you're committing to. So, complicated example, but I'll walk through it. First, the attacker creates some malicious Perl code. And it doesn't actually have to have a shebang on top. I'll explain why in a second. But a little Perl script that basically does what that echo one-liner did. Then they add that as payload to the description field in a .v file. They don't commit it as a delta to that file. they put it in the description field. The reason being that field is high up in the .v file, and I'll show you why that's important in a second. Then they add a generic-looking one-liner that says, to the log info, this is the actual hook that gets added, is all Perl execute %r foo.c, v. This is the file in which the description field has that Perl payload. And the reason that this works is that Perl-x will take that, it's going to execute that file as Perl code. And using the description field, it means that in the RCS file format, it turns out that it's high enough. And I think Perl with -x is like basically it's going to look for the first thing that looks like Perl code and it's going to execute it. And then at the bottom of our payload, which I kind of glossed past, we have an exit. So the fact that the rest of the file contains a bunch of goo that is not valid Perl code doesn't matter because we exit cleanly. And now basically the same moving parts as before. When Alice commits to this repository, that's step 4. The embedded Perl code gets executed and the public key gets added. Now again, this is just one example of how you would use this attack. You could use any kind of interesting payload you wanted, but it's an easy example. We'll go through some for subversion. A lot of the same things can be done in subversion as could be done in CVS. So alter an existing revision. The subversion on disk format, totally different from CVS's. Instead of .v files, 1-to-1, we have revs files and rev props files. Every time you make a commit, a revs file gets added that was the delta of your change, and a rev props file gets added that's the properties of your change, like the log message and things like that. Again, though, if you're careful to respect the format, you can change an existing on-disk rev and things will be happy and you'll get away with it. You can either change history as long as you unchange it by the end of by current, or you can change you can change some history and have the change propagate all the way forward as long as the cumulative set of deltas still add together without conflicts. So, for an example of what the on-disk format looks like on subversion, we're checking in foo.c. This is our safe code that does a blah blah blah. It prompts the user, does an fgets to get a message from the user, and then prints fsit. So what gets written onto the repo when you commit code like this, a revs file gets created that contains delta svn blossom header goop, the payload of the change, and then some trailing goop of metadata about the change and whatnot. Now, that metadata includes the size of the patch file, the size of the patch file plus some of its metadata, and then checksums, MD5 sum and SHA-1 sum of the payload. This is about as effective at preventing tampering as publishing MD5 sums or SHA-1 sums of files on a website that are up for download. If somebody can replace the file on the website, they can replace the checksum on the website. So the attacker takes that and modifies the payload to have gets instead of fgets and changes the metadata to show the corrected sizes and the new checksums. I'm doing a little bit of hand waving here. There's like 1 or 2 other details that I had to trim out, but it is basically that easy. And then the next time a developer checks out that code base, they're going to get the modified doctored version. And again, they're not going to know anything's amiss. All right, I don't have an example of actually walking through Alice and Bob and Mallory for this one, but that's okay. Now, just like we can move tags in CVS, we can move them in Subversion. There's one tiny relevant difference, which is that in Subversion, basically any change to anything in the repo creates a new revision. So when you create a tag, the act of adding or the act of removing a tag counts as a revision. So in this scenario, we have, we started with revision 15, because I picked that number randomly, and it was tagged. that creation of that tag would have been revision 16. Then in QA, if a flaw is discovered and fixed, so the new version is 17, and then the tag is moved to 17, and that increments the counter yet again. And then again, developers continue forward moving, building the next great feature set. Once again, an attacker with just remote commit access, unless you've done something special, which is possible, can delete and create tags. So they do the same thing they did in CVS. They delete the tag that points to revision 17, and they add a tag that points to revision 15 with the same name. Boom, they're done. Now when version 1.0 is checked out, the bad code is going to get checked out. A little bit of a graphical depiction here. So we started with a flawed revision. We fixed the flaw. We created a tag called release 1.0 that pointed to the fix, and then we continued on development. Then the attacker, in what is basically one action, but logically it's actually two, deletes the existing release 1.0 tag, and then makes a new 1.0 that points back to the original flawed revision. And again, the developers are none the wiser. All right, so abusing hooks in Subversion is not as easy as in CVS because the hooks are not actually managed. Like in CVS, CVS root is a special directory that every CVS repository has, which you can manage through regular commits and whatnot. In Subversion, the hooks directory is different. It's not managed under SVN. So the attacker needs some other way to manipulate the hooks. Maybe they need file system access to the repo. Or maybe they need some kind of management interface. Once again, code hosting sites probably give their users who own projects the ability to manage the hooks for their own project. If you can manage the hook for your own project, you can take over the accounts of other people committing to your project. As long as that actually gets you something interesting. Like if you imagine a completely stovepiped environment where every single repo is its own chroot, let's say, then it doesn't matter if Mallory can take over Bob's account for Mallory's repo. If Bob's account in Mallory's repo isn't the same as Bob's account in Bob's repo, then you're safe. I'll just say I hope that's the way it's done by those public sites. Attacks against Git repos. So I mean, CVS and Subversion are old news and boring, and they're old and busted. This is the new hotness. Actually, it was the new hotness like 10 years ago. Now it's pretty much the de facto thing everybody's using. Okay, so a bunch of people raised their hands for Git earlier. How many of you would call yourself Git experts? Okay. Oh, there's a couple people. Well, you might be lying, but I'll give you the benefit of the doubt because there were only 2 of you who raised your hands. If like half the room had raised your hands, I would accuse you all of being liars. I'm more and more convinced that Git is like quantum physics. If you say you understand Git, yeah. So a little bit of background on how Git stores stuff in the back end so that I can then show how those other examples do or don't fit. So Git stores interesting things in objects, which is special files, or packs of objects. But that's a distinction we don't really need to dwell on. Objects are, there's 3 kinds of objects. Mostly. There's commit objects. Whenever you make a commit, you're creating at least 3 objects. You're creating a commit object, which contains some metadata about the commit and a pointer to a tree object. And then the tree object has 1 or more pointers to blob objects. The blobs are where the actual code is that matter. Like the code that you're committing is in the blob. The metadata about it is in the commit and the tree. And objects are named for the SHA-1 sum of their contents. So, and when Git is told, hey, I want to check out, whatever, it walks the tree of pointers to reconstruct or to give you the version that you asked for. So a revision will be pointed to by at least 1 other object. The head pointer is actually not a special binary object goo file. It's just a text file under refs that contains the checksum /name of the object That's the head revision. And then you can walk backwards from there to piece together all the rest. And I'm going to consistently use only like a 4-character short name for revisions, but Git internally uses the full length of a SHA-1 sum as the object name. So first question, since we had a lot of success in CVS and Subversion, can we rewrite an existing Git object, just go scribble on it on disk and then have, you know, interesting things happen? Basically, no. Because the objects are named after the checksum of their contents, changing the contents of an existing object without changing its name, for the most part, requires breaking SHA-1. And even though SHA-1 is considered broken, it's still a really, really hard problem. And you know, so good luck with that. On the other hand, Git offers a lot of advanced functionality that gives you room to hang a rope to hang yourself, and gives the attackers ways to manipulate you in other ways. Yeah. So one example of that is a replace object. So I really vastly oversimplified earlier. And if you know Git well enough, you know that, and that's fine, because we only have an hour and not 6 weeks. And I don't think, like I said before, I don't think my brain is big enough to really hold all that's possible. But so replace objects are a little weird, but what it basically means is you can arrange so that when Git looks for a particular object by reference, by its hash name, it is told, no, that's actually this other object. Use that instead. They're rare but possible in normal use, normal operations in Git. So in a scenario here, we have an initial commit that contained safe, boring code, and a tag named foo that pointed to that. Then another revision was added. The new revision was buggy, was insecure. Foo still points at the original, which was safe but had fewer features. And then another revision is added that fixed the bug that was just introduced. Head is now, you know, pointing there. Head always points to, well, head. So now the attacker uses a replace object to say, when something looks for 11FB blah, 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 I want you to actually give them the bad revision of 81D6 blah, blah, blah. So when the developer references foo by name, they get the bad code. In this case, we have not changed the tag, but we've replaced the object that the tag points to point to another object. There are some caveats with trying to actually do this. Because Git replace objects are relatively uncommon, they don't necessarily get automatically propagated by like a regular push or pull. So I am hand-waving past some of those. Just in case you know that, I'm telling you that. But it is nevertheless quite surprising to people, if they haven't thought about this before, that this can be done. Now we can also just relatively, you know, standard thing now. We can do the same kind of go ahead and delete a tag and re-add the tag to point to the wrong thing, no problem. And I don't think I even bothered to diagram it because it is really simple. It's the same deal. Just delete the tag that where it used to point to and point it at the other broken revision. If people trust the tag name without, you know, checking which revision it points to, you can get them. So, and all you need for this is the ability to push and pull. Now, that is often a high bar for the public code hosting sites. Typically, for instance, in GitHub, your workflow doesn't include pushing into somebody else's Git repo. Your workflow includes forking it, making your changes, and then saying, hey, please pull my changes, and fold them in. But, hang on a second. Yeah. Some people need liquid courage. I need liquid awake. All right. And something that's possible in all of these, but I didn't bother with examples for them for the other two, is adding a new revision by hand. Basically, we're going to put a new head revision in place. Now, why might you want to do that? Well, it goes back to hooks. A lot of organizations use hooks as a quality control check or a sanity check. When you commit code, your code is supposed to get emailed, your diff is supposed to get emailed to all the developers on the team, and they can all eyeball it because they all totally read their email, and it's not spam that they delete at all. Or it goes an automated review process where if the code, I mean, first of all, if it doesn't compile, but second, if it gets flagged by any kind of automated checker you have, then it gets rejected. That's cool. Or it requires sign-off by multiple other developers before it's allowed. Or the log message is required to mention the bug tracker ID that it fixes, or the configuration change is required to reference the change control ticket. Whatever your local policy rules are, they're typically enforced with hooks. So the ability to get code into the repository without those hooks ever firing can be very interesting to the attacker, because the stronger the hooks are, the more the organization depends on the hooks working and being enforced. So, and actually because of that, developers who are in an environment where they know all that stuff happens may be more likely to not strictly check every time they do a pull or they do a SVN up or whatever, to actually manually read the diffs of what just changed in the code that they pulled down. They're like, oh, the code checker has me covered. Now, note, in Git, there's a no verify option to a push that will allow you to turn off one of the hooks on the server, the pre-commit hook. I'm assuming for this example that it's that's not enough for the attacker. Maybe it's a different hook that the attacker wants to bypass other than pre-commit, or maybe this infrastructure doesn't allow no verify, like the server side is configured not to let somebody bypass hooks just by saying that. So, all right, add a new revision by hand. Well, here we have our standard, safe revision that's existing in Git. In this case, this is the head revision, and we have on the repo server objects in the object subdirectory for each of these: the commit, the tree, and the blob objects. And ref's heads master contains the name, the checksum of this revision that's good. And we're assuming that there's some paranoid hooks in place on the repo server and that the bad guy wants to bypass them. So they can. If they can just plop files in place, which again, in order to be able to push, you have to have file system permissions to do that, unless you're going through some kind of fancy two-step. So if the attacker is able to do that, they can just write new objects into their object directory tree. No problem there. Happens all the time. And update master to point to that instead of pointing to the previous one. Now the next person to do a poll is going to get the bad code, but the files just magically appeared there from the perspective of the repo server. So the hook's never fired. All right, so this is all hypothetical, right? Nobody's ever done anything interesting with any of these. No code repositories have ever been harmed, and yeah, and well, so Operation Aurora is one of the first ones that a lot of people have heard about because it hit so many companies and a lot of big names. We know that the attackers were targeting SCMs, in fact, in the companies that they were targeting. We are mostly assured by the people reporting on themselves that nothing was modified, they think. Things were just taken, they think. Yeah, I totally trust my new corporate overlords to tell me everything and be accurate and actually know the full extent of how badly they were compromised. But Operation Aurora is really just one big blip in a large field. And not pictured here is 2014. I'm going to need a smaller font. Now, I'm aggregating here ones that are where all we know is that a distribution server was compromised. That happens actually kind of often. Like a web server gets owned, or a CDN gets owned, or DNS or DNS gets hijacked, and therefore people going to www.codehosting.com are going to the wrong place, and so on. I'm in this slide covering both of those and ones where the actual repos were compromised. But we do know that the actual repos were compromised for sure in some of these cases. Nmap runs on a Linode hosted environment, and Linode got owned pretty badly. And one of the things they went after was Nmap. Now, I don't know for sure what, if anything, was done to the SVN repo. I think it was SVN at the time. Hopefully, you know, Fedora had good backups and restored, and we're all happy, right? And GitHub, I kind of made reference to this earlier. There was a Ruby on Rails bug that allowed authentication bypass in Ruby on Rails web apps or something like that. Thanks. And the guy who discovered this was trying to report it to the Ruby on Rails people, but there was some like friction politically. It was one of those great situations where everybody gets along really well and everybody has everybody else's best interests at heart. So he got frustrated and used the vulnerability in Ruby on Rails to compromise GitHub to add himself as a committer to the Ruby on Rails project on GitHub to commit the fix. All I want to say is I hope he was the first person to use that vulnerability against GitHub. And yeah, we have no proof either way. So some possible mitigations. I'll run through some of these. None of them are perfect. None of them are easy, but all of them may be possible. Integrity monitoring. So traditional integrity monitoring tells you when stuff changes. And if it's things you don't expect to change, that's great. But repository contents change all the freaking time. Now, some subset of a directory tree on a repo server may not change regularly. For instance, in Subversion, the revs directory should have new files added to it, but they shouldn't change. Unless you pack the repo, in which case a whole bunch of them get vacuumed up and put into big blob, big pack files. So I guess even that's not true. But other things like rev props can change legitimately if you allow like somebody to update a log message because they typoed or something. So traditional integrity monitoring is just way too painful. We need integception. We need to go deeper. We need to understand the context of the data inside each of those files, understand what exactly has changed and what is the meaning of the change, and is the meaning of the change something that is okay, or is the meaning of the change something fishy? Another thing we could do is smarter hooks to address the ability for somebody to push new revisions onto head. We should do some kind of close the loop on make sure that every revision that you get when you check the data out matches. You have proof that the hook's fired every time each revision was added. Problem is, this is harder than it sounds, because if what happens when a code is committed is the hook runs as the person who commits the code, and if the attacker has the ability to write stuff into the repo as a valid developer, then they have the ability to run hooks as a valid developer, which means they have the ability to run parts of hooks. So they could run the part of the hook that your accounting tracks, but not the part of the hook that actually would have caught them. So you can do some kind of privilege barrier, and I am hand waving for sure. But let's say all that happens when the hook fires is that some privileged process gets run. I don't necessarily mean root. It could be a dedicated, repo admin user, and that repo admin user does all of the things. And so if you're not the repo admin user, you can't do some of the things. You can only do all or nothing. If you do all, you've lost any advantage because the hook just fired. There's some not purely technical things we could do too, like when a developer's usually working 9 to 5 and suddenly they make a change at 3 o'clock in the morning, maybe that's fishy, especially if you work in a secure facility and nobody should be able to physically get into the building at that time, and you don't allow VPNs. Maybe you have policies about what log messages should look like, and commit messages, and comments in your code and stuff. And there have been a couple of projects actually that have worked a little bit on that. I know Bruce Potter has one. His company, not Shmoo, but you all know him from Shmoo, but his company Pontitech has worked on a thing on another DARPA project that maybe can detect that, or maybe all it'll do is detect that your developers are drunk. Now maybe that's also worth knowing. Yeah, well, right, when they're sober. How can you tell when they're sober? So one thing that could help us is if you had all of your commit messages were signed, PGP signed and verified. Now, Git has that feature, which is great. This doesn't prevent everything, but it does raise the bar for the attacker. The attacker is not enough to compromise the SSH account or the GUI web interface blah for something. They have to actually compromise the developer thoroughly enough to get their PGP private key. And they have to burn the accounts. They can no longer lie about who it was that made a commit because the signature won't match that person. Although it's only as good as the enforcement. And even though Git has PGP signing, there's not an out-of-the-box hook that verifies or forces it. And if you're in the habit of checking for signatures, you have to also make sure that you're only allowing the signatures by keys that you want to be allowed to sign. It's not enough to just say, does it have a signature? Yes. Does it check out? Yes. Is it by one of my developers? No. Okay, that's a problem. That's pretty much it. We will be blogging about this some more, and I'll probably post the slide, and if it wasn't too terrible, I'll post the video too. Any questions? Oh, there's a couple in the back, I'm sorry. So blue shirt and glasses first, and then you. I think you were asking, I could barely hear you, so tell me if I get this wrong. He was asking of the projects that I listed, what percentage were using some older, simpler repo type versus ones that were using, let's say, Git. Is that right? I don't know. That is a good question. Some of these compromises predate Git, so obviously they would not have been running Git. The companies that have been owned, I don't know if they've talked about it. I know Aurora, like I said, targeted SCM, but it targeted Perforce, the commercial users of the Perforce SCM. I believe that it wasn't a vulnerability in Perforce per se, but it was like attackers were getting file system access to the repo servers or something. But that is a good question for me to try to track down. And then, sorry, what was the next question? Have we looked at Mercurial? Not enough. If somebody knows enough about Mercurial to be able to comment intelligently on how many of these things, or perhaps others, it might be susceptible to, that would be great. Please come find me. That's my email address, my PGP fingerprint. Thanks again to DARPA. I should have said this at the beginning. So thanks to DARPA and the Cinder program and Mudge for getting this work started and funding some of this research. That being said, I am not speaking for DARPA, or they didn't approve anything that I just said, so on and so on. Yes?
In the instance where you have to move into tags, there's no auditing for that?
So the question is, when you move tags, is there auditing for it? There can be. For instance, you can have hooks that notify you when tags move, and you might notice it when you SVN up or git pull or whatever to see like what tags have been added or changed. But nothing out of the box will like scream at you for sure. And then any other questions? I have a couple if anybody wants to try to answer them instead. Okay, thanks everybody.